In learning any type of network application, the first thing that has to be brought up is the prerequisites, which in this case would be binary and hexadecimal numbering. Now, what I'm about to show you is something that you haven't been just recently introduced to, but it's something you should have known when you were 6 years old, and that's pretty much how to count. So understanding how to count is the prerequisite knowledge for this type of training. The first thing we're going to talk about is decimal numbering. And with decimal numbering, it all comes down to how you read a number. So when looking at the number 346, some people would read it just as it says, 346. I've heard 346. But really, how you read that number depends on how the placement value is laid out to you. And with decimal numbering, the placement values are very simple. There's a ones column, there's a tens column, and there's a hundreds column. Now, therefore, when reading this number properly, you read it according to its placement value, which is 3 hundreds, 4 tens, and 6 ones, or 346. If we were to add this out a little bit further to the next placement value, it would be 1,346. That is how you read a decimal number, always according to its placement value. Another concept that has to be introduced when looking at numbers is the number of combinations. And since we're looking at decimal, decimal is a 10 base number, which means that just like we have our placements are ones, tens, hundreds, thousands, we have to look at the number of combinations per placement value, which means if I'm looking at this same number as far as the number of combinations, then that number 6 that is in the ones column would have 10 discrete combinations. It could either be 0 through 9, and that would be the number of combinations, which means if I wanted to look at the total amount of combinations that 2 digits would give me, it would be 10 times 10 or 100 combinations. Just like 3 decimal placement values, which would be 1,000 combinations. 4 would give me 10,000 combinations. Now, a quicker way to understand decimal numbering would be to look at the patterns that crop up with this type of way of thinking, or the way you would number them, or the way you would count them. And when looking at that same ones placement value, you could say that the number 6 has 10 different combinations, or you could look to the next placement value, and that would tell you the number of combinations of digits that precede it, which would be 10. Therefore, if you look at 2 placement values, the number of combinations would be 10 times 10 would be 100. That would be the next placement value. Just like with 3 digits would be 1,000 combinations, or the next placement value, which would be a thousands column. Another pattern that would crop up is if you're trying to figure out how high one of these placement values could count. Now here I have all of them maxed out to the max value they can be, which would be 9. But if I wanted to look at a shortcut to find out what the physical count of what a number would be, I could look at the next placement value and subtract 1 from it. Which means in this case, the maximum count that one decimal digit would give me would be 10 minus 1, or 9. If I wanted to look at the max count that 2 digits would give me, it would be the next placement value, which would normally tell you the number of combinations, 0 through 99, minus 1, which would be 99. This happens because 0 is a number, and it normally takes up a place that you are not used to. Therefore, when looking at the maximum count of 2 digits, it's always going to be the next placement value minus 1, which would be 99. If I do the same thing for 3 of them, it would be 1,000 minus 1, which would be 999. And that would be the maximum count that 3 decimal digits would give me. With binary numbering, we're going to exercise the same habits we did with decimal numbering, except it will yield a different placement value for each of the digits as well as a different number of combinations. But we're beginning to start talking about binary. We have to understand some of the basics, which is a binary digit, or a binary number, is usually separated into 8 discrete values, of which one of them individually is called a bit. When we put 8 bits together, they form what is called a byte, as it is often called. When reading a binary digit, you do the same thing as you did in decimal. You must read it according to its placement value. For binary numbering, the placement values would not be 1, tens, hundreds, thousands. it would be 1, 2, 4, 8, 16, 32, 64, and 128. When trying to interpret what these values are, you usually read a binary number by all 8 bits. And depending on which value has a 1 marked on it, usually goes against the count. Which means if I were to put in digits here to form a number, if I mark the 128 place, there's a 1 marked on it, which means I count it for 128. 32 with a 1 on it equals a 32. There's an 8 place for 8, and there's a 4 marked for 4. So if I add up the bits together that are marked 1, it would be 128 plus 32 plus 8 plus 4, which is a decimal equivalent of 172. Therefore, a binary number of 10101100 would equal a decimal 172. To try this again, we reset the values, mark the 16 place, the 4, and the only number when counted can form an odd number, the 1. We add them up to be 16 plus 4 plus 1, or a 21 decimal equivalent. Therefore, the binary number 000010101 would yield the decimal equivalent of 21. But just like with decimal, if we're going to complete the numbering system, we also must address the number of combinations that a specific binary number gives me. Just like in decimal, if we look to the far right, which would be called the least significant digit, we see that the ones column, or the 1 placement value, has 1 value, which can be a 0 or a 1. Therefore, there are 2 different combinations for that 1 placement value. Times 2 for the next placement value, which together, 2 bits, would be 2 times 2, or 4 different combinations. In order for me to make my point about a number of combinations, just to keep things on track, if I were to look at, say, 2 binary digits, a 0 and a 0, the total number of combinations would normally be what? 2 times 2, which would be 4. But if I wanted to make my point well known, it would be 0, 0 as the first combination, 0, 1 as the second combination, 1, 0 as the third combination, and 1, 1, which would be the fourth combination. Therefore, the 2 times 2 would be 4, and these are all 4 of the combinations. If I wanted to make the point of 8 combinations, once again, I could have 3 bits, which would be 2 to the third power, or 8 different combinations, or 2 times 2 times 2. If I wanted to show you all 8 combinations, just to make the point final, it would be 0, 0, 0, 0, there's 1 combination, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, or 1, 1, 1, which would be 8 different combinations, 2 to the third power, and there's your 8 different combinations. If we were to play this combination out all the way to the 128 place, we see that it's really 2 to the 8th power, or 2 times itself, 8 times, which would yield a max combination of 256 for 8 bits, or a byte. Just like in decimal, we have patterns to find out the number of combinations, and if you want to know what the number of combinations of a digit are, you could always look to the next placement value. And just like we said before, if you look to the next placement value, it should describe the number of combinations of the digits that precede it, which means 1 bit gives me 2 combinations. If I wanted to know the same for 3 bits, you would look to the next placement value, which would be 8, and that would describe that 2 to the third power, or 2 times 2 times 2, would be 8 different combinations. If I did it to 2 to the 7th power, that would be 128 combinations, and if I did it for all 8 of them, there's your 256 combinations. Just like when we addressed with decimal, we had to deal with the physical count, or the max that a number could be. Therefore, we go back to the pattern we used before, which was that a binary number 000000011 would physically count to 3. Because we've maxed out both values on the right-hand side there to 1, 1, that would be a 2 plus 1, which would be 3. You could look to the next placement value and subtract 1 from it, which means you could have 3. If I wanted to do the same thing for 4 bits, you could look to the next placement value, which would be 16, minus 1 would be 15. If I did all 8 bits, 1, 1, 1, 1, 1, 1, 1, 1, would be 256, or the next possible number of combinations to the left there, or the next placement value. The next placement value would have been 256 minus 1, which would give me a physical count of all 8 bits, or a byte, to be 255. When applying the binary concepts to hexadecimal numbering, the goal is to try to take a long string of binary numbers and reduce them, or read them in a smaller format. In this case, the goal is to reduce the binary number 10110110, or the decimal equivalent of 182, to only be viewed as 2 discrete values. In order to do this, we have to take the binary number and divide it in half. Since hexadecimal is a 16-base number, which is 4 bits, 4 bits with the number of combinations equating to 16 distinct combinations, we have to read the binary number in 2 sets of 4, therefore changing the placement value from 1248 out to 128 to 1248 twice. In other words, each binary number would be viewed in sets of 4 bits apiece. So the number to the right would equate to a 4 plus 2, or a 6. And since the number to the left would equate to the number 11, which would be 2 discrete values all by itself, the goal is to only have that number represented by 1 discrete value. Therefore, a lettering system is used for numbers that are over 9. 10, or A, would be a 1010. B would be 11, or 1011, and so forth. Therefore, the 1011 would equate to being the hexadecimal equivalent of B, or Bravo. We would read it as 0x Bravo 6, 0x meaning that the following notation is in hexadecimal format, which means we would read the Bravo 6 as a value of 4 bits and then another 4 bits, or 1 byte. So continue with the conversion. We have 0x alpha 6 echo 5, which means the following notation is in hexadecimal format as an alpha 6 echo 5, which means each one of the discrete values would represent 4 bits. The A, looking at the cheat sheet on the bottom left, would represent 1010, which would be an A. The 6 would be 0110. The E, or echo, would be 1110, and the 5 would be 0101. Therefore, the binary equivalent of 1010011011100101, instead of attempting to read that number as 2 separate binary digits, could be easily condensed to the hexadecimal equivalent of 0x alpha 6 echo 5. When applying this to a real number, such as the one shown here, that is 48 discrete binary digits, we would need to condense this to something more readable to the human eye. So when reading that number in a hexadecimal equivalent, starting from left to right, we would read them in 4 bits apiece. 0, 0, 2, 6, 0, 8, E as in echo, 9, 1, and because those are all 4 ones there, it would be an F, because F is always 4 ones, 1, and then finally 5. Another way to view this, to show you that the following notation is in hexadecimal format, the number or the long string of 48 bits there would be, the 48 bits would be shown as 0x002608 echo 91F15. For instance, looking at my computer, you could see that one of the MAC addresses, or the physical address, that is assigned to my network interface card, which will be reviewed in a future lesson, would be a hexadecimal value of 002608 echo 9 1F15. But really now, you know that that is 48 discrete bits that is read by the computer as a physical address.